imagine that you have a binary file and you don't create this file, you don't control this file, you're a sort of third-party consumer of it. But you do want to apply some of your own changes to that file. Maybe you want to insert some bytes into the stream. Maybe you want to simply replace bytes or delete them or extend the whole file. Whatever you want to do, you kind of need some way of expressing the way in which you patch that file. Now, this is a problem that comes up in a number of different domains. Basically, anywhere you have a binary blob, usually as something that isn't open to the world, that requires some reverse engineering, usually this is going to come up. And one place in particular where it has come up is in the gaming and emulation communities. And that is because it remains legal to actually make digital copies, backups of games that you own. And this is especially common in cartridge-based games. We have literal ROM chips inside that you can dump the contents of, pack it into some kind of ROM format along with metadata that allows it to be emulated on a digital system. Now, many people from these communities are not only interested in sort of preserving games in this way, but also applying their own spin on things, either creating new content or adding translations for games that never sort of made their way from Japan to Europe or the United States. And in general, people kind of like to get creative with existing content. And so this is a problem that's come up in the emulation community and been solved in multiple ways. And that's kind of what I want to explore today, and maybe in some future videos, are some of the solutions that were found for this. And there are many formats for patching binary files out there. Some of them are domain specific, so they sort of make use of the fact that a certain kind of binary file is formatted in a certain way and can be taken advantage of. And some are much more general. And the one that we're going to look at today is called IPS, and it is quite a general format actually. It was made for really made for classic cartridge-based game patching, but it is indeed a generic format. But it does make some trade-offs, and those trade-offs mean that it is not well suited to tasks outside of this kind of very simple, relatively small file size patching, even though it is generic. So let's actually jump over to the spec and see how it is described. And as we go further through the video, I actually want to build an implementation of a patcher, basically referencing the spec and building a patcher. And then I want to patch an existing game using a patch that can be found on the internet, and just see how it works. And I think there's something to be learned just about kind of the design of these kind of formats, some of the trade-offs that you might have to make. And if we look at a second format in the future, we'll see how this kind of basic approach grew and evolved into more sophisticated approaches that still deal with the trade-offs, but in a more sort of flexible way in many ways. So without further ado, let's take a look at the spec. Okay, so as close as I can possibly understand it, this is the specification. This might not be the original specification, but it does describe all the information that we need to know in order to both read and write these kind of patch files. And it gives away enough. Whether or not it is the official spec, I don't know, but it seems to be, as far as I can tell. So let me zoom in a little here. I'll try to keep my camera out of the text that we're looking at. Basically, IPS is a very simple format. It basically has a header, which just kind of identifies the file, and then is made up of a series of what it calls records. And these records basically describe how to patch over a particular byte in the original ROM file. Now you'll probably notice something kind of straight away here. Since that's the only kind of operation we can do, we can't actually sort of insert bytes, meaning we can't sort of have some of the ROM, then insert some specific bytes, and then have kind of the ROM continue. That's not really possible in this format. What you have to do is to just, you can only really patch over bytes that are already there. You can write beyond the ROM, and many patches will do that because many games are kind of just adding assets, and so they're just sort of extending the size of the ROM and extending the sort of address space that the ROM can handle, and stuffing more assets kind of on the tail end. But yeah, that's kind of a limitation there. And then after these records, we get to an end of file marker, which basically just says that the file is done. And that is it, actually. So beyond that, a record is actually made up of an offset. So that sort of tells us where to look into the original binary file, like what byte are we addressing. And it is a 3-byte or 24-bit number. And because of that, it has an effective limit on how many bytes it can actually address. And as you'll see up here, they can't patch a file larger than just under 2 gigabytes. So that is again a limitation. It's not a limitation that really makes a big difference in emulating or in emulation of sort of classic 16-bit type consoles, because they certainly didn't get to that kind of size. But you can imagine you couldn't patch a modern game with this format, even if you wanted to. Patches themselves cannot be larger than just under 8 megabytes, which is also pretty small. So you can't really add much more to a ROM than that. Although that can technically contain more than 8 megabytes worth of data, because there is a small amount of compression being done in this format, although it is kind of really minimal. Okay, so with that in mind, our record structure, we can keep an offset. It's a 24-bit number. Then we can have a size field, or we have a size field, and that is 2 bytes. So we have a 16-bit value, and that basically, that's defining well, how many of the coming bytes are going to be part of this record. And then of course we have the data itself. So a record is a variable sized field, but it is at least 5 bytes. Well, it must be at least 5 bytes. Presumably in this format you can have 0-sized records, but that's something we actually have to talk about, because there is an even more specific extension to this, and that is that the small amount of compression that can be done is using something called run length encoding. Now, we've talked about a binary format for storing images before on this channel, Koi, and Koi actually employs run length encoding. So if you've seen that video, you kind of have an idea about how this works already. But run length encoding is effectively the simplest form of compression you can imagine. It basically says, here's a pattern. In this case, it's 1 byte. So here's 1 byte, and I want you to repeat this a certain number of times. So that means that if you do have a long run of zeros or FF or whatever, you can actually encode that in much fewer bytes than you would if you had to write the whole thing out by hand. But you can imagine that since there's some overhead, and I haven't explained the overhead yet, so I probably should, the way that we can recognize a record that has run length encoding is that the size field is 0. So if the size field is 0, then we're going to actually read another 16-bit value, and that is the real size. And it is specified to be a non-zero value, so I guess you can't have 0 length records, which makes sense. But basically we can encode a certain number of of runs here. And it also doesn't really make sense for this to be 1 either, because then you would also just, I mean, I guess they allow for it, but it wouldn't make sense for you to just place 1 byte this way, because you could do it here with fewer bytes. So this is the effective way that this works, and that is actually it. That's all there is to this format. There's really not a whole lot, but you can do a lot with that. The one last detail that we need to note is that the encoding of the 24-bit number is essentially big endian. So the first byte is the most significant byte, and then the next byte is the sort of next significant byte in the sequence, and finally we have the lowest byte. This is well, I mean, you always have to make a choice, but these days I think you see little endian in a lot of places, so it's an interesting choice to have gone with this. But this format, I'm not sure if this was made in 1998, but yeah, it's been around for a while in that case, and little endian probably wasn't quite as popular as it was then as it is now, because of the prevalence of ARM. Okay, so the idea is going to be that we're going to implement this patcher. I have a ROM, which of course I've legally dumped myself from my own hard copy collection. And I have a patch which I've downloaded from one of the myriad emulation sites out there that provide patches and ROM hacks. The ROM in question is Super Mario World. It's a game that I spent a lot of my childhood playing, and playing the ROM hacks is actually, well, for me it's very frustrating because I'm not good enough to play them effectively, but they are fun nonetheless. So that's kind of it. Let's actually get into the code. Okay, so for those of you that have been with the channel for a while, this language will be somewhat unfamiliar. This is the first video I'm making since having transitioned the channel away from being specifically a JavaScript and TypeScript channel into one where we can explore many different kinds of languages and environments. And so for today, we're going to write this in C. And what we're going to observe, most likely, is that although C is a low-level language and, you know, we're dealing with a binary format, it is my opinion that C is probably not the best language for this. I think that's probably true of a lot of things with C these days, but nonetheless, it is probably one of the most important languages in the world. I think it's useful for pretty much everyone to learn C at some point, to some degree. But yeah, I mean, that's what we're going to do. And I'm sure that there are, you know, I actually think this could be more effectively written into, like, say, TypeScript, because it can effectively deal with this kind of binary formats just fine. And we wouldn't have to mess around with memory management quite so much. But the C program will be fast, so there's that. I mean, any program would be fast at these kind of file sizes, right? We're dealing with an 8 megabyte patch. I mean, if we were dealing with a 2 gigabyte input file, then we might have problems, but Super Mario World is not 2 gigabytes. Okay, so what we have here is a directory. I've set up just the most minimal skeleton for this project. So I have a source directory here with a main file, which just has the most minimal possible main implementation. And I've brought in just a file that I bring around and drag around to different C projects, which is basically just a couple of things that make working with files a little bit nicer. So the thing that we're going to use here is a function called read to end, which basically lets us read a file into a buffer, and it gives us back the buffer and a size that comes along with the buffer, because in C, even if you have an array of something, you don't really know how big it is at any time. So this just gives you back a nice, convenient, wrapped up object, so to speak, that has the data ready for you to access and the size. And that's pretty much it. That's the only file I really want to use from function I really want to use from that. So I've brought that in as well. And there are two header files which we'll talk about a little bit if you're not familiar with C. But effectively in C, header files are kind of where you put just declarational kind of information, and this information can be shared between multiple C files. And the reason is effectively because when you write C and when you compile it, you generally compile each C file individually, so that you don't have to compile every file every single time you make a change. And what this means is that if one file is sort of sharing something that's in another file, it has to have a way of knowing about it, and typically the way that that's done is header files. So you kind of put all the information which you kind of want to share around, you put that into a header file, and then that can be included in the various different C files that you need to use. It doesn't matter so much for now. We're not going to focus on the sort of compilational parts of this, or really how C and translation units work and all of that. That's not really important for today. But I'll try to cover it when it comes up if necessary. Okay, so what I also have here is a copy of the Super Mario World ROM. Of course, legally dumped. I do own a physical copy of this game. I of course have the facilities here to dump that. So that is my legal backup. And I have a patch, or I have two patches, but the one that we're going to use is Return to Dinosaur Land, because that is a much more substantial patch. And these are two IPS files. So effectively, we can open this up, and well, I'll open it up here in Bewitched. So let's say Bewitched, patches, Return to Dinosaur Land. And what we'll see here is the header, which is actually just the word patch in all caps. And then we can start to see the records encoded in here. And it's just a bunch of binary data describing all these transformations. So there's not really much for us to see there. Okay. Other than that, there are a couple of other directories here. There is an obj directory and a bin directory. Those are going to be where some of our sort of compiled artifacts ends up. The bin file will contain the main program, kind of the main thing that we build. And the obj directory will contain the sort of object representation of the different C files as we compile them. There is also a build script. This is not a makefile or anything. This is just the world's simplest shell script, and all it does is kind of, describe the flags that we want to pass to the compiler, and some commands for basically finding all of the C files and the header files, so that we can give the compiler all the information to find where all the files are. You have to do that in C. It's much more explicit in that way than, I guess it's more implicit actually in that way than something like TypeScript, where if you require another file, you really have to require the path. Except if you're talking about npm type resolution, where actually a lot of weird stuff can happen, and Node has some quite specific ways in which it goes and looks for a file. But in most cases, that actually just works. Okay, enough of all of that. The last file I have here is a diagrams draw.io file, and this basically just has the representation of the IPS file and of the records themselves. So we can reference this if we need to. Okay, the first thing I'm going to do is I'm going to create a header file. I always think it's useful to create header files because that's just like in TypeScript, you normally start with building your types and kind of design, like thinking about what your function signatures are going to be, right? I'm going to have a function that takes in this and returns this. And I like to do that in the header file. So that's usually the first place that I will start when I'm writing C. So I'm just going to call this, I guess, IPS.h. And because of weird stuff in C, you have to kind of guard your header files. You have to make sure that they don't get included multiple times, because the way in which header files are included is basically a copy-paste operation. So this guard makes sure that files don't get copy-pasted more than one time. So what we do is we check if there is a kind of preprocessor symbol called IPSH. And if there is not an IPSH, then we're going to define an IPSH. And then we have to kind of close this whole statement. So in the end, we're only going to do the stuff in the middle here. We're only going to copy paste it if this hasn't already been defined. And the first time that it gets defined, of course, we're not going to copy paste it anymore. All right, that's probably clear at this point. So what I think I'll do to start is just, well, let's define first the IPS header. So the IPS header is, like I said, just the word patch, which is pretty straightforward. And looking at the spec, the end of file marker is also just the literal word EOF, or the abbreviation EOF. So the IPS EOF, or end of file, is EOF. Now, these are useful because we can use these as a very simple sanity check to make sure that the that the file is correct. So let's just make a couple of functions here. Let's say I'm going to include a header here called common.h, which I think I didn't mention, but common.h just includes some other C standard library headers. So things that we can name our types sensibly, like standard int and standard bool. Standard IO is for doing things like reading files and printing to the screen. Malloc is for dealing with allocating and freeing memory, and string is in there because there are, well, obviously we often need to deal with strings, and in C you can't just compare strings with like regular equality and that kind of stuff. You have to call certain functions, but also for whatever reason the string header also contains the function memcopy, which is literally memory copy. Take this memory and copy it to over here. I still don't really understand why it's in string, but I guess it's some sort of traditional or like long historical reason. But yeah, those are functions that you often need. And again, this common H is something that I drag around to different places, or at least I recreate it almost every time. Okay, so we're going to have a function that returns bool, and this function is going to be called IPS underscore header valid, and it's going to take in, well, in order to determine whether this header is valid, we need to take in kind of the data buffer of the patch. And the way I'm going to do that is I'm actually going to pass in this sized pointer t type, which is a structure that has a pointer to some data, which are all just bytes, and a size. And I think that will be a nice format to take this in. It allows us to make sure we're not going to read outside the bounds of this. We're not going to read outside the bounds of this array, because that is effectively what this pointer is. It's just an array of bytes. Okay, so we're going to take in a sized pointer t, and of course we don't have that because that's in this file x header. So we're going to take in a sized pointer t, which I'll just call patch, and that's it. And we can actually mark this being const because we're not going to change this pointer at all. We're actually also not going to change any of the things inside it, but that's neither here nor there. So let's just implement this function. Let's start out writing some code already. So I'm going to make a corresponding C file called IPSC. The first thing we'll do is include ips.h, and then we're going to implement this function. Okay, yeah, okay, so these are working correctly. Sometimes my editor doesn't, when I make a new header file, it doesn't understand that those definitions also need to come into the IntelliSense, but this time it did. So how do we check this? Well, patch, this should actually be a pointer to a sized pointer t. We'll get into pointers and things like that shortly, but basically we've got access now to the data and the size. So the first thing we're going to want to say is, do we have enough bytes to actually read the the patch like kind of thing? So we need at least 5 bytes to be in this file, otherwise we can't like kind of safely check this anyway. So we're going to say patch size is like greater than or equal, or if it's less than 5, then we can just return false at that point. Really easy. The header is not valid, the whole file is not valid. That's not good. And for the other part, we need to return. We need to use one of these string comparison functions, and they are called str for string, and then you would use CMP. There's actually a version called string n CMP, and that's the version you should actually always use, because that basically says, and there is a maximum sort of length of characters that you should try to read from each of these strings. Yeah, you should always provide lengths of how big things are in C, because C doesn't check that, and you will get all kinds of memory bugs because of that. C is famous for its memory bugs. Okay, so the thing we're going to compare is going to be patch data. So we're just going to read the first bytes of this thing. And the other thing we're going to compare is this IPS header, which I defined already as being the string patch. And then the third thing is going to be just that we shouldn't compare more than 5. Now, you would think that you could just return this, but you can't, because string n compare actually returns an integer, and it returns basically 0 if it's successful, and it has some other it returns -1 and 1 in specific circumstances that are, meaningful in those ways, but we basically want to know if it's equal, so we're going to check it against 0. So that's it, that's our header valid. So let's actually go into main. Let's include ips.h, because that gives us our references to our functions. Now you see that we have 2 files which reference the same header file. Those will be compiled separately, but now the main file is aware of the functions that we've written in this file. So that's why we do that. Okay, so what we're going to do is we're also going to get the file x header here, and I'm going to make a couple of defines for let's have the patch file. So the patch file is going to be, well, it's in patches, and the patch name is return to dinosaur land. So copy that. Alright, and then the ROM file, that is going to be in ROMs, and it is this one. Okay, so now we can read those 2 files. This file reading function is not it's not exhaustive in the checking. It does assume that these files exist. So that's something to keep in mind. Like in the case that your files might not exist, you actually should probably modify the functions a bit so that they do what they should. But in this case, I'm just going to use the basic version, which assumes the file exists and assumes that we're going to get back a sized pointer of t. Actually, I think I might have written this so that the files aren't assumed to exist. Oh, that is right, yeah. But it does mean that you would have to check your sized pointer t for null of the pointer. That's neither here nor there. We're not going to check for null because we know these files exist, but you should in a real program actually do that. Okay, so the first one is going to be the patch file. So we're going to call read to end. We're going to pass in the patch file, and you also have to pass in the flags that you would pass when trying to get a file handle in C. So in this case, we need to pass in that we're reading a file and that we're reading it in binary mode. Okay, so now we have the patch file. The first thing to do, or it's not a good habit to be in when you're writing C, is to understand that this function actually allocates memory. And because it allocates memory, you should sort of immediately write the free that goes with it. Otherwise, you'll end up with bugs. So I'm going to write the free here, and the allocated memory is actually in, it's going to be on patch.data. So the data here is actually a uint8 pointer. So it's a pointer to some bytes in memory somewhere, and we have to tell the operating system effectively that we're going to free those bytes afterwards. I mean, yeah, whether we actually have to do that or not is really up for debate, because we effectively don't need to give these bytes back until the end of the program, and by the time you close this process, this is a single-threaded process, the operating system will also free all the memory anyway. So you don't really have to do it, but you should do it, because that's not going to be the same in every function that you write, that you understand that, you know, the end of the function is the end of your program. So, all right. And coincidentally, of course, if you're in a JavaScript, like if you're in the JavaScript world, and JavaScript actually, you know, of course, you don't have to deal with memory, but behind the scenes, the just-in-time compiler and the whole interpreter and VA or whatever you're using, that actually does have to allocate memory. And it's basically is going to be creating functions, and those functions are going to sort of have lifetimes. And so at the end of the function, like things that you have created that go out of scope are actually going to be kind of freed in that sense. So we're sort of just emulating that here, although in C you have to do it explicitly. So we're going to free that data, and now kind of let's just make this the cleanup area at the end, and we'll put all the cleaning up kind of stuff there. So we're going to read the patch file, and we're going to assess if well, let's just say if IPS header valid, and we'll say if the header is not valid. And here we'll pass in patch.data. Actually, you know, we need to pass in the whole patch object, which is the size pointer, and we need to pass in a pointer to this thing. So we need to pass in the address that we get for that. A little bit confusing because we're talking about like kind of pointers to things with pointers, but that's the way it is. We allocated this thing on the stack inside this function, and so we have that. We don't have the address of it. We need to pass that as a pointer. You can always take an object that's not a pointer and kind of point to it, right? So that's what we're doing with this and symbol. We're saying memory address of this thing, pass it into the function. Okay, if it's not valid, we'll just print something. So in this case, we'll print header invalid xting. And I'm just going to return 1 here. Like, you need to understand that by returning at this point, we're not freeing the data, so that's a problem. And this is why, especially in the kernel, you'll often see them do this thing, which is a lot of people think is really bad, and it is in some ways bad. But like, you know, like make literally a label at this point, and then instead of we would go to error, And then what that does is skips all the code in between and just goes and frees the memory. But we're not going to do that here. That gets hairy, and there are a lot of ways for that to go wrong. So we're not going to do that. We're also not going to be too concerned about the whole thing. I'm saying that and then talking way too much about the memory stuff. Okay, so let's just compile and run this program and actually get a sense of if we're reading a valid patch. That's the first thing. And if we're not, I've probably done something wrong. Okay, so we can run the build shell. You can see that it executes a series of commands. So we execute GCC like 3 times here with all the C files. And we just create object files. So we've compiled each file individually. And then at the end, we call GCC again with all of the object files, and we link them together into one thing called bin main. So that's the actual kind of the process, kind of compile everything individually and then assemble everything together at the end. And it's at that moment that if you had referenced a function that you said exist but didn't because it was in some other file and we couldn't find it, this is the time that you would see that error. Okay, but it seemed to run, so we can assume, of course, that it's fine. And we didn't see any output, so actually the program is working at this point. We didn't see this header invalid. Great. So now we've read the header, we can actually start reading records out. And I'm just trying to get a well, I already know that the IPS format, it has quite a fatal like kind of flaw in this way. And the fatal flaw is that it doesn't anywhere kind of in the header or any special section, the header is literally just a magic number actually, but it doesn't specify the length of the expected file after patching. And that's kind of annoying because what it means is that in order to figure out how large the file is going to be at the end, you kind of need to read all of the patches, or sorry, all of the records, you know, all the way to the end and kind of figure out how many bytes you've gone to. And once you've read the final record, then you can figure out how large your file is going to be at the end. But we can't do that because well, that's the way we're going to have to do it basically. We're going to have to read all the records first, kind of build a data structure that kind of keeps track of all those records, figures out how big the final file should be, and then we can go back, iterate through the records again, that time actually applying the patch. So that is what we're going to do now. So let's read the records. So let's go back to the IPS header and actually create a type to hold these records. And this type is pretty much going to mirror this. It's going to mirror the sort of basic version of the record. I'm not even going to make any kind of special version of the run length encoding because we can just cram it into this one by figuring it out in the moment and then just stuffing it into this format. And this is going to be kind of when you're building programs, there are multiple axes that you can think about optimizing along. You can optimize for space and doing things like where you only iterate once, so that's kind of optimizing for time. You can optimize for space, and we're not really going to do any of those. So we're going to basically iterate through things multiple times when you probably could do it once, and we're going to use a whole bunch of memory that we probably wouldn't have to do either. Neither of those things matter because we're talking about running this on a modern machine with like many gigabytes of RAM, and we're talking about small files here, so it literally doesn't matter. But if it were a larger system, those things would start to become important, and you would start to want to make trade-offs. Like maybe you want to say that running through all the records, you don't want to build up the data as you're going. You want to iterate through each record, and you want to apply that patch in the moment. And in that way, it means that you're going to kind of have to figure out if you need to resize your output file as you're going along. That's a trade-off you can make. I'm going to try and avoid all that complexity for now. So getting back to the record, I'm going to make a type here. We can, well, in C you have something called a struct. It's what you would think of as an object in JavaScript. And because of C weirdness, we have to wrap it in this. We don't have to, but I'm going to wrap it in this thing called a type def, which allows us not to have to write some redundant information. So we're going to create a type def. It's going to be called IPS underscore record underscore T. And you actually have to put that twice. And it's a struct. And again, I'm not going to get into the details of this because there is some nuance, and you know, if people know C, then I already know that there's going to be comments like, you don't actually have to do this, you don't have to put this name here, you don't, like, I know all of that stuff. But this is the way I like to do it for various reasons that I'm not going to go into now. Okay, so what do we need in here? What do we need in a record? Well, what do we have in a record? We have an offset, a size, and data. So that's what I'm going to put in. The offset is a 24-bit number. We don't have 24-bit numbers in C. You certainly could make a 24-bit number. It's just not worth it. I'm going to make a 32-bit number, and it's going to be const at the time we create it. Actually, I'm not gonna do all the const stuff because that's kind of worth doing afterwards, after you've figured everything out. Go back and work out what's not going to change and then const it, and then that's a nice hint to the compiler about how things do or don't change throughout your program, and then it can generate better code. So we're going to have an offset. We're going to have a size. The size is actually just a uint16, so we won't waste space there. And then we're going to have data, and the data is actually going to be a pointer to just some memory. So like this structure is going to hold some memory that's been allocated, and therefore anytime we have one of these structures, we need to remember that each structure needs to free the memory that it holds. So we're going to have a uint8t pointer to some data. That's it. That's going to be our structure. And I think what we'll do is we'll write a function called how do we do this? There's actually going to be one more thing in this structure. And that is going to be that we're going to make these records a linked list. Now, linked list is a thing that you hear about, you know, in interview questions for languages where it just makes zero sense to do that. In C, the reason it makes sense to do things like linked lists is, well, one, because you have to allocate all the memory yourself all the time and do all that kind of stuff. But two, it doesn't have any kind of generic data structures. So if you want to kind of build a generic set of something and grow it, well, you kind of need to figure that out yourself. So what we're going to do here is create a pointer to another struct, which is this IPS record. And now, because of stuff that I didn't actually want to get into, we're going to actually have to reference it in this way. Struct IPS record T pointer. And that is because there's kind of two names for this thing. There's this name where you say struct record, and there's this name where you just refer to it here. But because we're actually defining this name outside, and that name kind of is what this whole thing is, we can't use that name yet because we don't know about it effectively, because we're kind of in the process of declaring it. So we need to use the big long name that I don't really like to use. But we'll do it in this case because it's kind of self-referential, and that's just going to be a pointer to next. So each record is going to hold a bunch of information, and then it's going to point to the next record in the series. And when we get to a record that has a pointer that's kind of not valid, a null pointer, then we know we're done. We know we have the last record. So yes, what I think we're going to do is we're going to write a function that is going to return an IPS record T. It's actually going to return a pointer to an IPS record T. And that means that when we free a record, we need to free the memory that holds the record and the memory inside the record. And I'm going to wrap that up in a function so that we don't have to remember that, but this is the sort of stuff you get when you work in C. Okay, so this function is going to be called read record. And what we're going to take in is a reference to the patch. A reference to the patch and a position within the patch. So we need to have an offset. Let's call it offset. And we have this type called size t, which is size t, I think on most platforms, or at least on most kind of 64-bit platforms, that's just defined to be a uint64, but it's not guaranteed to be that. So depending on what your platform is, size t will change. But effectively, size t is the thing you want to use if you're addressing into something. If you're like looking into an array or something like that, you want to use size t because that talks about sort of that's an integer that's not going to overflow when you try and look into something, because it's kind of like the biggest representation on the platform. Hope that makes some sense. Okay, so this is the function, so let's go and implement that. Okay, so reading a record. I guess what the first thing we're going to want to do is just create this record, kind of allocate memory for this record. Yeah, I think that makes sense. So I'm going to say that we have an IPS. Like the first thing we're going to do is create the thing that we return. So this will just be, we'll call this the record, and we're getting a pointer to something, and that is because when we call malloc, the thing that we ask for to allocate us memory, that gives us back a pointer. It actually gives us back something called a void pointer, which is like if you use TypeScript, that's kind of like an any. That's like, you decide what this thing has to be, which is useful when you're talking about memory, because like we want to say that this little bit of memory you've given me, this however many bytes of memory you've given me, this is this object, this is this structure, it should be considered to be this. But actually it's just memory, right? So it could be anything. So that's kind of down to you. When you allocate memory, you don't have to say what it's going to be. You do that by kind of assigning your any onto some specific type, and you actually can just keep it being a void pointer and pass void pointers around. C is pretty loose like that. Okay, so that we have to have a certain size. How big is this record? We don't have to count the bytes ourselves, and actually that wouldn't always work. We use something called size of, and then we can just pass in the record size. So officially, malloc can fail, so you should check the output of malloc. Like you should check it if you've got a null pointer, but that only happens in pretty weird circumstances, and it's not going to happen to our program. So in the end, I'm going to return record. I'm not going to check for null pointers here, but be aware if you're writing a bigger program that does more important things. I'm doing all this because it's disclaimer. I don't want anyone to take any of this as like legal advice or medical advice. It's kind of on that level, right? Like legal advice and medical advice, they're both sort of like risky enough that people straight outright legally can't say do this thing. And I kind of feel like C programming is like that. Like you shouldn't give people C programming advice. Everything is at your own risk. Okay, so the record is going to contain random data now. Malloc doesn't zero the memory or anything for us. So I think the first thing we're going to want to do is kind of figure out like the fact that next should get set to null by default. It should be a null pointer. And the rest of the fields we're going to fill in ourselves. Okay, so let's do that. We're going to read the first 3 bytes of memory. That's what we're going to do now. And when we read those 3 bytes, I guess we need to take in a pointer to an offset. Why do we need to do that, you ask? Well, let's think about this. C functions, or, functions in general, as we generally think about them, there are exceptions, but generally the way we think about functions are that they have one return type and they have a bunch of inputs. Now, in C, because you can pass pointers around, what that effectively means is that something you pass into a function, you can also write back out to it, right? Because they've just given you the memory address, so you can just go back and do something to that memory, which means that, what it means that arguments that you pass in can effectively be return values as well, in a way. And that's often used in C when you'll have a function that the return type is the success or failure of that function, and you are expected to pass in a pointer if you want certain, like, kind of the actual return value of that function, so to speak. I'm kind of not using that pattern here because, well, kind of, even though I probably should, actually, I probably should, because, of course, when we try to read a record, we might actually hit the end of file. We could handle that somewhere else, and maybe I'll do that in this way. But yeah, probably it would be better to write a function that returns whether it was successful or not at reading a record, and then expect the caller to pass in a pointer to a record, which effectively also pushes back the memory as a dependency injection kind of thing in that way. Yeah, if that makes sense. Like right now, this function allocates memory, whereas we can expect the caller to do that for us, and then we don't really have to, well, it's kind of pushing the problem back one place. Well, I'll cross that bridge if I come to it. I'll go down this path for now. So we're going to read the next 3 bytes of memory. The first thing we should do is actually check if there are 3 more bytes of memory. Because if there are not, no, I'm going to expect that to have been done in the previous function. I realized that I should have worked some of this out ahead of time, but this is what I'm going to go for now. So kind of if we call this, what's the word here for an invariant? If you call something an invariant, it makes it sound like much more technical already. But like an invariant is something that we expect to be true for this function. Like if you call something outside of the invariance, then it's no longer valid. An invariant for this function is going to be that the next thing is not. You know what? I'm going to go back on all of this. I'm actually going to I'm going to return true or false for whether this was successful. And we're going to take in the offset. And we're going to take in the target record. We're going to take in the offset. So, yes, we're going to expect the caller to do that for us. And therefore, in the end, we'll just return true. We also don't need to do that. Yeah, okay. So this is the new definite, like the new signature for this function. It's also the annoying thing about C is that, you have to, if you do something like this where you change your function type, you have to usually go and do it in 2 places, at least 2 places. Okay. So now, we're not expecting anything to have been checked ahead of time. So we actually want to check, is this the end of file? And I think the way I'm going to do that is quickly write another function up here called IPS is end of file. We'll take in the patch, we'll take in an offset. And what we're going to do is we're going to do another string compare effectively. So the first thing is going to be that the offset plus 3 should not be bigger than the size. So if offset and offset plus 3 is bigger than patch size, then yes, it's the end of the file. Although it's also not valid. That's something we'll assume files are valid for now. Notice here that this is a dereference, so this is how we actually like kind of take this from being a pointer to something to being the thing inside the pointer. So offset plus 3 greater than patch size, return. Then we're going to do a string compare at patch data, but not just patch data. We want to look at the offset and we want to compare it to end of file. Oh, of course, we need to dereference that here. And this should not be more than 3. And so what we're doing here is just making sure we have enough bytes to even do this. And then we are just comparing the data. We're kind of using it as an array at this point, which you can do with pointers. And we're passing in our own offset. And then we are returning whether or not the thing at that offset is the end of file marker. Okay, that's it. So then when we read a record, the first thing we want to say is if IPS is end of file, and then we need to pass in our patch and our offset. Then we will return false. We did not read a record. But if it's not the end of file, then we can start to read. So we want to see, do we have enough to read these 3? So we want to say if we basically need to do this check a whole bunch of times. So if offset plus 3 is greater than patch size, then there's actually not enough. There isn't enough memory to read this, so we're going to skip it. I'm just going to kind of do all of these kind of checks like this, so they're just all on one line. So we don't have enough to read this this thing, but now we know we have enough memory available to us. Like we have space to read. Not in allocation terms, but there are enough bytes left in the patch for us to actually read this. Now we can check, or we can read them into a number. So let's make a uint32. We don't really need to do that because we can just stuff it into the record already. So record offset is going to equal, and what we'll do is we will say it is patch data offset. So that needs to be shifted up by 24 bits because again, like this is a big endian thing, so the first byte that we read is actually sort of the most significant sort of third byte of these 3 bytes. So we're going to do something like this, and the compiler will clean this up for us. And I guess we can plus the offset at each moment. And I know that we should always do this as well. Okay, so this is kind of concise, but what we're doing here is we're reading each byte of this offset. We're reading it into the record, and we're just sort of shifting and ORing it into place. So we're making one number, and we're just sort of using bitwise operations to get them lined up all together. And along the way, as we read each byte, we're also incrementing our own offset, which is a pointer, so it's going to be written back out to the global offset of whoever called this function. So they're also going to know that we've moved this offset along. So now you can see why these things are done as pointers, hopefully. Okay, so now we've read an offset. That's it. Now we want to read a size, so we need to do this check again, but this time we need to see if we have 2 bytes available to do a size. Otherwise, now we can read the size, and the way that will look is record.size, and then first we shift up by 8, and then we OR in, and we don't need to do a shift. Okay, so now we've read a size. So at this point we need to check if it's a run length encoded thing, because the way that's going to work is that this field will be 0 if it's run length encoded. So what we'll do is we'll check for 0, then we know it's run length encoded, we can read the real size, and then we can actually figure out the data buffer after that. So if record size is 0, if the record size is 0, then we are going to read again in the same way. So we'll just sort of copy this. And you can see that you might want to kind of wrap this up into a function or a macro or something, but I'll leave it like this for now. So then we read into record size properly, the actual size. If it's run length encoded, we're going to do that, and the size comes afterwards, and then the 1 byte of data. So that's something we need to keep in mind down here, is that the data, well, we'll read that separately. So we've read the size now, and now we know how big of a buffer we need to allocate inside our record for our data. So we need to use malloc here to figure out how many bytes we have, and that's actually just going to be record.size, because in either case we want to have a buffer of this correct amount of size. Now you can imagine that you could have your record type keep track of if it is run length encoded or not. But since we're doing this whole thing of scanning through all the records and then going back again, what I want to do is just have all of that normalized, so that when we go through the second time, we're literally just applying records in the same way each time. Nothing special happening. Okay, so we've allocated memory, and now what we can do is either read or sort of copy the memory that we have inside the patch into this, or we can just set that memory to be the 1 byte in each case. So we're going to say if we're run length encoded, then the next byte, so we need 1 byte, let's get it like this. UN8T, we'll just call it byte. So we're just going to read the next byte. And then we are going to use memset to simply set the memory. So we're going to set n bytes of S to C. I mean, you could use longer names here. That would make sense. So the first thing is S. So this is the thing we're setting. So what we're actually going to set is record data. Whoop. We're going to set record data and C is the value, so that's going to be our byte. And then this is the number of bytes to do, so that is going to be that is going to be record size. Yes, that's going to be record size. Because we're setting the whole allocated buffer here. So that's the simple case. Otherwise, what we actually want to do is we want to copy out everything in the patch from now on, or for patch size amount of sorry, not patch size, record size. For record size number of bytes, we want to copy that out of the patch and into this data buffer. So we're going to use memcopy for that. And first we need to check if we have enough bytes for it. So we need to say offset plus record size. If we have enough for that, then we can actually do this operation. So memcopy. So we're going to copy n bytes of source to dest. I mean, source and dest, we've actually got real names here. So the destination, where is this going? Well, it's going into, where are we going? Record data. The source is actually patch data plus the offset. And the size is record size. Okay, and then what's we saying here? This actually we need to dereference it, of course. I'm going to wrap these up in parentheses. And then offset plus equals record size. If you're looking at this and you know some C code, and you're seeing all the times that we use this arrow, which means read through this pointer, and thinking, oh my god, this code is going to be so inefficient because we're reading through this pointer all the time, and you're going to have to do all this memory indirection. Well, the compiler is probably not going to generate actual reads through these pointers, because we haven't told the compiler that these are volatile pointers or that there are any other kinds of restrictions around them. And therefore the compiler will probably, hopefully, be able to tell. Although now I'm saying that, it might actually not, because it might think about doing pointer aliasing. Well, we'll see. But my thought is that probably it's not going to need to do that in all these cases. And even if it does, it just doesn't matter. Okay, so this part is going to be set the data in the buffer. We're figuring out run length encoding. So now, as far as I can tell, we've set the data, we've set the size, we've set the offset. So the final thing to do would be just to make sure the record has a null pointer in the next, and the whoever is calling this can assign that, and then we'll just return true. So now we can read a record. Let's do that. Let's try that out. So let's create a record here. So there's going to be IPS record T, and we'll just call it record. And we don't initialize the memory or anything because it's all going to happen in this function. Then we are going to do something like this, IPS read record. We're going to pass in our patch, and we need an offset, so let's also make that quickly, size T offset. We're going to start at offset 5 because we want to be after this header. I'll pass into the a pointer to the patch. We're going to pass in a pointer to the record, and we're going to pass in a pointer to the offset. So all of this stuff is stack allocated, so we need to get the memory address of each of these things that we pass in. Of course, when we actually read all the records, I'm probably going to do that in a separate function, and then that function will take care of handling and allocating all the memory for the records. So if was successful, then we can say, I guess we could just put that here, we don't really need the variable. And if it was successful, let's print a message. So we read a record, offset equals, and we'll print this as a hex number, so OX 0. It's 24 bits, so we kind of want it to have 6 places, and it's hexadecimal. So we're going to have an offset, a size, we want it to be 16 bits, so it's going to have 4 numbers, and it's going to be hexadecimal. And do we write the data out at this point as well? Well, let's just do this for now. Let's just say that it's that. Let's also put a new line at the end of that error, and then we need to put in the data here. So that's going to be record dot offset and record dot size, and then we're going to clean up. And actually, we need to clean up the. We'll do it just for the sake of it, although we need to get rid of this in a minute. We'll clear up the record.data. So that was an allocation we did. So let's build and see what I did wrong. So I did something wrong here. So string m compare, basically we have the patch data, and then we're going in by an offset. Yeah, this is actually a problem here. I should just add these things together, because this now is getting the actual data at that point. So that is a problem. I'm glad the compiler is telling me. It is a warning, but it is definitely a real error, but to the compiler that's a warning. So the way to deal with this is just to do this, and then when we add this to this pointer, this will stay as a pointer and not read the actual value of the information at that point. Okay, so let's try that again. No errors this time. So let's try to run. And we read a record that points to offset 0100FF, and it has size of 1. Let's actually peek inside this patch and see if that kind of makes sense. So let's open up Bewitched again. Excuse me. Patches. That is not the patch that I want. I want to have return to Dinosaur Land. There we go. Okay, so this is patch, PATCH, and then we have 0001FF, and what we see here is 0100FF 01. So this doesn't make a whole lot of sense to me, because what I would have expected is to see 0001FF, but instead, wait, let me look at the spec quickly. Let's return to the spec page. The header, note that this patch string is not null terminated. So that 0 that occurs after the header, after the string patch, that is not like null termination. That's kind of what my first idea about that was. Somehow we're just reading the information in the wrong way. So when we read the offset, we take the first byte, let me just quickly think about this, that I've set the offset in the right place. It's kind of weird to me that this is ended up in this order. Yeah, this doesn't make tons and tons of sense to me. it's also weird that I can't scroll back up now. 0, 1, 0, 0, FF. Really strange. Okay, so we started at offset 5. So that's 0, 1, 2, 3, 4, and then 5. And then we checked, could we read 3? And then this first offset, we said set at bit 24 down to bit 16 or bit 17, I guess. 24 down to 17. No, it was 16. Set this to be whatever the value is we read at offset, and then increment offset. But this is post increment, so we would read 5 at this point, and then we would shift that up. And then we read the next one, and we OR it in, and then that should point here at this one. So that should be 0, 1. And then finally we OR in the last byte. I'm confused about what's happening here. We're not overwriting that at any point. It seems about right. I mean, throw a printf in here just to see if something weird happened in between. Actually, in fact, you know what I'm going to do? I'm just going to put a breakpoint down, and we can debug this with the debugger, which is the easier way of doing things. So we should have an offset of 5. We do. Let's put a breakpoint here that is record offset. So at first it's 0, and we can actually print this in hex already. Okay, so it actually seemed to have read 0 there. Okay, so patch, is it data inside this? There's data. So yeah, okay. So it reads the string patch, but if we actually look at byte 5, we should see 0. Yeah, and we do. We see 0. And it was also 0, I believe, in bewitched patches. So yeah, it's 0. And then we read here. Zero, zero, 0, 1. Oh, I think I'm actually... Yeah, I'm shifting these into the wrong positions. That should be going to 16. That should be going to 8. That's why we're getting something weird here. So that is an error, but just a stupid one on my part. Okay, so let's compile and run again. And this time we see, yes, 0, 0, 0, 1 FF. Okay, and a size of 1. And I didn't actually assert that the size we would read would be 1, so 0, 0, 1, 1, and then we read 1. Okay, and then that byte would just be a 1. So we could introspect that, but I'm actually fairly confident that that should work now. So this function, this is kind of doing the heavy lifting. And now we need to write another function, which is going to be read records, right? Read all the records, and then we want to build this nice big linked list. Okay, so let's do that. We'll write a function called read records, and it will essentially take in the same information, but this time it's just going to handle all, it's going to abstract that out. So they will provide in a first record, an initial record, which they will take care of allocating on the stack or whatever, and they're going to pass us in the offset as well. Okay, and yeah, we can return bool for this as well. So IPS read records, and we're taking the same signature, so okay, so we'll return true already. Okay, so this is the place where we need to check for end of file, effectively. We only really need to check for end of file. Although, aren't we doing that here? We only really need to read records, yeah. So we can read a record. That will tell us if we were able to read a record or not. And if we've stopped reading records, we simply, we're done. I guess if we can't read the first record, I guess the number of records we read would be a better thing to return here. Like, how many records did we really read? That's going to be like a more useful piece of information to the outside world, because I guess effectively there could be 0 records in a patch. It's a useless patch at that point, but you could just have a header and an end of file. I don't see anything in the spec that seems to suggest you should have at least 1 record. It's just variable, right? It's the number of records may vary. It doesn't say that there is at least 1 record, as far as I can tell. At least the spec is ambiguous in that way. Okay, so we're gonna do this basically. We have to allocate a record ahead of time. So this is going to be our record. Let's do this. This new record equals malloc size of IPS record 2. Then we're going to say while read records patch new record and offset. Like while this is going true, we're just going to keep going as well. So we're going to read a record, and it may or may not be true. So in the case that it is true, well, we read a record. So records read ++. I'm just thinking, like for the very last record, when it doesn't, I guess for the very last record, we can just free this already, because it wouldn't have, like, we can always just do this. We don't need to check, like, whatever the last record was, like, we allocated it. We need to allocate actually every time. So let's do this. We need an initial allocation, and then we're going to run this function and read a record into that initial allocation, and then at the end we kind of need to allocate a new record, and then what we'll actually do is we'll do something like this, so that at the very end of this while loop we always allocate before we start again, and then that way when we go into the function, the very last time it will be invalid and we'll free that record at the end. So even if we don't get a record the first time around, we're going to free it, and every other time. So that takes care of that. We read a new record. Okay, well, we also kind of need to keep track of our previous record, if that makes sense. We're always going to have a previous record. Let's do this. Prev record. And the previous record in the beginning will just point to the thing that's been passed in to this function. Like the original first record that gets passed in from outside. So that's our original previous record. So what we actually want to do here is we want to say our previous record and then we want to assign its next pointer to be the new record. So we're already kind of passing that along, and then we want to say that our previous record now equals the new record. So that is also fine, so that takes care of that. We allocate, and in the end we return the number of records we read. I actually think that this is it. This is all we need to do. So let's try that out, I guess. Okay, so we have the offset, we have the first record. To make life easier, I might actually just make this also like allocated on the stack, then we can just free everything. So size of allocated on the heap rather. That means that we need to not pass a pointer there, and we need to do that. So then we need to pass in, we need to free record, data, and record, but we're going to need to free much more. So I think what we will do is we will write another function, which will be called, I'm just going to make it void, and it's going to be called IPS free record. And then we're going to take in a pointer to a record. And this is the declaration, so implement that here. You can implement code in header files, but it's generally not a good idea to do that for the whole copy-paste reason that we discussed earlier. Okay, so although it does make distributing libraries easier, which a lot of people do these days, they're called header-only libraries, which means that if you have a project, you can just import this header. You don't have to set up some special build system. It will literally just copy-paste the code of the library into your program. There can be problems with doing like that. That can be slow in certain circumstances, but it is a very, very easy way to distribute your software. Okay, so we're going to take in a record. And what we're going to basically need to do is kind of walk through this linked list, freeing stuff as we go. So let's have, we're going to need to have a previous pointer. And that will be null, I guess, in the beginning. And what we actually kind of want to do is we want to say that while there is something, like, while there is something to be pointed to, and I guess, does this make sense? Or I guess we could say like just while record, because record is the pointer itself. So if there's something in record, do we need a previous actually? We do need some sort of temporary thing here. What we're going to do is we're going to say that like we've got this record, we can already free record data. We can free the data inside the record. Then what we want to do is we want to free this whole record, but first we need to keep track of the next record. So we're going to say temp equals record next. Then we can free the record. Wait, does this make sense? Yeah, because the next thing is what we want. Free the record, then we can say record equals temp. So what's going to happen is we free the data inside, then we keep track of what's going to be the next thing. We free this whole record, then we can kind of set our like current record for the while loop to be the next thing. So if this was null, like then we'll end the while loop. So this should free all of our records for us. So now we can replace this stuff with IPS free record, and we'll just pass in this, which makes life way easier. Okay, so now what I want to do is I just want to read the records, and I want to say how many did we get. So size t, records read equals read records, and we can just print how many we read. Records read okay. We read one record, so that's not quite right. I know that that's not right. Yeah, well, I'm still calling read record, so that actually sort of does make sense. It's funny, that's such a C thing, right? Because this thing returns, if you have read record, it actually returns bool, and true will just get cast to 1 when you're setting it to some integer, so we see 1 record. That's kind of a funny bug in itself there. Alright, we build again, we run, and we got a segmentation fault, which is fun, but here we read 1967 records. I'm kind of interested at what point this broke down. So let's just see if the general mechanism is working correctly. So I'll put a breakpoint here. We can go in. There we allocate. And then we're going to read a record. So let's just make sure that this works. I mean, it seems like it should. So is it the end of the file? Read the offset. So with the record here, we've got the offset. The size is trash right now because we haven't read it yet. Then we read the size. It's 1. Is it run length encoded? My guess is no, so that's false, which means that we're going to set the data manually. So we're going to allocate 1 byte, which is funny because 1 byte is less than the size of the pointer itself, quite a lot less. So if it's not run length encoded, we have enough to read. We're going to mem copy 1 byte from the patch, essentially. And we're going to do that into record data. So record data just contains the number 1. So apparently we read the number 1. And then we update the record size. Okay, so all of that worked. So then we read 1 record. We set our previous record to the next record. That's interesting, yeah. I guess for the first record, we don't need to do that. So that's probably not the issue, but now it's obvious that the new record the first time around is actually what we were given, because we memory allocated that. So there's no point just sort of allocating something and then stuffing it in. What we kind of want to do is do that. And now this doesn't really make sense anymore. We only want to do that if we read at least 1 record. So if records read is greater than or equal to 1, then in that case we're actually going to want to free that record. I don't think that would have been the bug, but that's kind of that. Now I'll put a breakpoint here. I just want to see if we actually get to this point, or if we segfault before that. So we're segfaulting at this point. We're writing into previous records next. Well, that makes sense now. That makes sense, especially in this case. Previous record is null. It wasn't before, so this is like a new bug. Previous record is null, so we want to do this if we have a previous record, basically. If previous record, then we set the next. Otherwise, well, in all cases, set the previous record to be the new record and then memory allocate again. Okay, so let's try again. Let's put another breakpoint down, or same breakpoint. Okay, so in this case we read 1967, so we can free the last record and return that. Now records read is 1967. We free the patch data, and now we're actually going to free this record. Now this is probably where things are going wrong, so let's take a look at what's happening here. We set temp to null while we have records. Now this is probably going to happen oh, I don't see any segmentation fault here, so I guess we got it. Yep, okay, that's good. We read 19,067 records. That seems accurate. So the final thing to do here is actually to patch the ROM. Because now we have all the information we need to actually perform the patch. What do we need for that? We need to read the patch file, so that's the ROM file. Let's read the ROM file. At the end, we're going to want to free the ROM's data, and I think what we're going to want to do is to also create an output file. So I'm going to call this the target file, and the target file will be ROMs, and this will just be patched. So this will be our patched file, and we're going to need a buffer. So what I'm going to do is, well, we're going to know the size of we're going to know the size now of how we're going to know how big we have to make this effectively. Annoyingly, the way that I'm gonna add one more thing to this function, which is going to be the last written offset. So let's go and modify this. Last written offset. So the reason I'm doing this is because we're going to need to figure out how basically the patch file can write off the end of the ROM. It can write more data than the ROM actually has. So we need to figure out does the when we create this target file, how big do we need to make this buffer that we're going to start putting data into? Do we make it does the patch make it bigger than the ROM, or is it just the ROM? So I'm going to pass in a pointer so that we can actually write back to what the last place that we wrote was. And actually, you know what? That's not even needed, because that's effectively what the offset is. Although it's not true, because the offset yeah, I don't think we need this. No, we do. Yeah, we do need it. Okay, so the last written offset is going to be whatever the current offset is, plus the previous record, the size. So basically, the last record has a certain size, and the offset is currently pointing to sort of the next no, this is not what we need. It's not to do with the offset. It's not yeah, I'm confusing myself now because we have the word offset in multiple places, but we have the idea of the target offset, like the ROM offset, and then we've got this offset into our patch. That's two different things. So actually this is previous record offset, like the patch offset plus the size of this thing. That actually gives us like the last place this writes. Yeah. Okay, so effectively, if this is bigger than the ROM buffer, this is what we would like to make. This thing plus 1 would be what we need to make. So now we're writing that out. The last written offset, we need to take that in, and kind of what we're going to need to figure out now is like, is this larger than the ROM size itself? So so let's make t target size, and we'll set it initially to be the ROM size, and we'll just say if last written offset plus 1 is bigger than the ROM size, or target size, it doesn't matter in this case, then target size becomes last written offset plus 1. Okay, and then we can create a buffer for the ROM. So it's the target. So I'm just going to call it target. It's going to be a uint8 t pointer, and we're going to malloc it, and it's going to be target size. And then because we've malloced, let's also free, and we're going to free target. Okay, so we've got the target, and now we just need to iterate through the records, and we start with this record. And so I'm just going to make another set of pointers here, call it current record. I could make a function called IPS apply patch, which would probably be better. I'm just going to do it here in the main function. This is going to initially point to record, and we're going to say while we have a record. And then at the end, we'll always be setting our current record to like whatever the current record next is. So as long as we have a record to deal with, we're effectively now saying, I guess we need a target offset as well. We're going from... No, this is not true. In the beginning, the target needs to basically equal the ROM. So effectively what we need to do here is to memset the s is the set m bytes of s, so we're setting target, and not memset, memcopy. So target is the destination, then we have the source. The source is just going to be rom.data, and we are going to do rom.size. So we're going to copy all the bytes of the ROM into the target. There are other ways you could do this, right? You could just also just reallocate the ROM buffer itself, and then you wouldn't need to keep this data in memory twice. This is kind of inefficient in that way, but I don't know. It also doesn't matter, right? We're talking about a couple of megabytes. So we are going to copy that all in, and now as we go through the records, we're assuming that anything in the target buffer, we can just apply the patches directly into the target buffer because it contains the entire ROM, and all the stuff on the end, we're assuming that the patch will stuff in there if there is space left over at the end anyway. Okay, so what we want to do is we just, each time we want to use memcopy, and the destination is going to be the target, target is a pointer, and we want to offset that target by the current record offset. And then the source of this information is going to be the current record data, and is going to be current record size each time. So there we go. Notice that these two together form a sized pointer t, so we could have also used that type here, but I haven't done that. So we're copying in, then we're just going to the next record. And then after this little loop, we should have the patch. So at this point, what we can do is we can write that out to a file. And now we need to, instead of using this nice like read to end, we need to use the C APIs. So we're going to have this thing called a file star, like file pointer. I'm just going to call it FP, and we're going to do fopen target file, and we're going to write this file, and it's going to be a binary file. Then of course we have something open, so we need to clean it up. We're going to fclose it down here. Okay, so now we have the file pointer to this file that doesn't exist yet. What we actually want to do is to write all the data inside target to this file. So what we can do is fwrite, and so I always need to look at these signatures because they're very verbose. So you have a const void pointer, which is restricted, which means something specific about aliasing. But yeah, they're all a bit like this, so you kind of get tripped up here. So the data that we're going to write, that's target. The size is going to be target size. And the number of times we're going to write this is going to be 1. So this is kind of, you can break this up into different chunks, but we're going to write all of the stuff once, and we are going to pass FP as our file pointer. So at this point, we've opened the file, written all the data of the target to that file, we've closed it up, we've freed all the memory that we allocated during this program, and I think we're done. So if I didn't write any new bugs, which I probably did, no warnings or errors, so that's actually quite a good sign. We don't have any prints in here, I realize. I'm actually going to put some prints in, so just to make the program seem a bit more entertaining. So at first we're going to validate the header, or actually let's report on what happened. So read a valid header. Then we are going to report how many records we read. Read records from patch file, and how many records did we get? We got records read. Creating a target ROM size bytes, so that's going to be target size. I also kind of want to report like the size of these things, so like opened patch file, and then like bytes, so that's just patch size. It's always good to have some, some information in your program, like read ROM file. Okay, so then we're creating a patched ROM of this many bytes, and then we applied patches, then we wrote to target file %s, and that's going to just be target file, and then in the end we're cleaning up, and then we're done. Alright, that's going to feel so much more dramatic when I actually run this. I'm just building the program again for no good reason. Okay, somewhere in here we have bin main. Alright, we opened up a patch file of this many bytes, we opened up the ROM file of this many bytes, we read a valid header, we read this number of records, we created a patched ROM size of this, which is significantly more than the actual ROM itself. We are applying the patches, we wrote the target file to patched SMC, and we're cleaning up. Okay, so now the moment of truth, the real moment of truth is, does this thing work? So I'm gonna switch over to another screen and show you the output of this. So first we're just gonna run Super Mario World as is. So that should work. It should come up on the screen now. So this is just the Super Mario World ROM as is, to give you a sense of what changes. So this is the game. Okay, and now I'm going to run, oh, this does weird stuff to my keyboard every time I run this emulator. For some reason it takes away repeated keystrokes, but no worries. Now I'm going to run the patch, checksum OK. Now this certainly looks different to me. It looks like this isn't actually showing up on the stream, so let me fix that. I don't know why that's happening. Alright, so I'm going to run it. And alright, that was way less dramatic than I was hoping it was going to be, because this just stopped working. But here we can see Super Mario World Return to Dinosaur Land. This was made in 2006, so presumably IPS patches are, oh yeah, it was 1998. But yeah, that's it. I'm not going to play the game, I'm not going to see what goes on here. But that's it. I hope you've really enjoyed this. I hope it's given some insight into whatever you may have wanted to get out of this, some idea about how ROM hacks work, or patches at the very least, but like this idea of binary patching. It was nice to write in a different language, to write some C on the channel, to think about some of the other concerns that you don't normally have while writing languages like TypeScript, and kind of how that changes even the data structures that you might think about using, simply because trying to do something like an automatically expanding array would be a lot more work actually than a linked list, and therefore like writing the bespoke linked list implementation turns out to be, you know, the sort of more straightforward thing. Anyway, I'm going to throw this code up on GitHub. I would love to know if you're inspired by this and you want to pick it up and make some improvements. Maybe you want to optimize some of the sort of bottlenecks that I've talked about here and make this program run so much faster and so much more efficiently. Maybe you've noticed a bug that I haven't, and you want to tell me about that. Anyway, I'm open to the feedback. So thanks for watching, and I hope to see you in the next one.